So we'll write the expression neatly here again. So the kinetic energy is 3 by 4 m r minus small r whole square with the dash square. And the potential energy is mg r minus r 1 minus cos theta. So now in our earlier theory we discussed that the sum of the kinetic energy plus the total potential energy is equal to a constant for a vibrating system. So only the switching of energy happens between the two modes, the kinetic energy and potential energy. So the derivative of kinetic energy and potential energy with respect to time will be equal to 0, because derivative of the any constant against any variable is 0. So we'll put this our expressions in this equation. So kinetic energy is 3 by 4 m r, and equate the expression is equal to 0. So for solving this equation, we'll take a differentiation. For the first term, it will come as 3 by 4 m r minus whole square, small r whole square is a constant. For theta, we'll get 2 theta dash, and again differentiation of theta dash with respect to time, d theta dash by dt will be equal to theta double dash. So here we'll get theta double dash plus mg r minus r small r is basically constant. Derivative of 1 will be 0, and the derivative of cos theta will be minus sin theta, and then differentiation of d theta by dt, that is equal to theta dash. So, and you get for differentiation of cos minus sin theta, so this sign will become positive here. This thing comes equal to 0. You have to take the common things out in the expression. The common things are basically m and theta dash. So we take this thing common, we get 3 by 4 r minus r whole square, and you will get it into 2. So here we get 6 by 4, and here we get theta double dash plus mg, m is taken out constant, g r minus r sin theta, and theta dash is taken common outside. Now you know that m can't be 0, mass of this object can't be 0, and the velocity also can't be 0, because we have considered a general time instance. It's not, we are not deriving only for the extreme position, and theta dash the velocity is 0 at only the extreme position. So theta dash also cannot be 0, we are deriving for general position. So this quantity inside the bracket should be equal to 0. So hence 3 by 2 r minus r whole square theta double dash plus g r minus r sin theta is equal to 0. We'll arrange this equation similar to what we have in a second order linear differential equation, homogeneous equation. So theta double dash, all these things will divide the entire thing by 3 by 2 r minus small r whole square. So you get 2 by 3 g, and in the denominator you get r minus r sin theta is equal to 0. Now this equation is not exactly same as our, where that equation was something like x double dash plus omega square x equal to 0. So here x was coming both places, here sin theta was coming. So in the start of the problem, it was given that we are solving the problem for small angular displacement theta. So if theta is very small, then sin theta is roughly equal to theta. The identity from the math class. So substituting this value for small angular displacement, you get theta double dash plus 2g by 3 r capital R minus small r theta equal to 0. So comparing that with the second order linear homogeneous differential equation, we get omega as equal to 2g by 3 r minus r. So like this you get your angular frequency. So which was the thing asked in the question. The real frequency of oscillation f will be equal to 1 by 2 pi of omega, that is 1 by 2 y of 2g 3 r minus small r. So here you can see the in the expression on the in the numerator there is G that is contributed to the in the numerator you have G which is contributed to the potential energy, and in the denominator you have the magnetic energy that is determined by the angular position. So R minus R. So this is something similar to what we get in a simple pendulum, square root of G by L. So 1 by 2 pi. In simple pendulum we get like that. In this case, similar to simple pendulum, we are getting G divided by radius. So this is our answer. We will take up one last example in the topic of free vibration. So here it is provided that a spring of stiffness 2 kilonewton per meter is suspended vertically and has two equal masses, each of weight 4 kg, attached to it. Now, if one of the mass is suddenly removed, then the system will not be in equilibrium, it will be away from equilibrium, it will start to vibrate. Then it is required to find first the amplitude and frequency of oscillation of the remaining mass. One mass is removed, other mass is remaining in the on the spring. What the amplitude and frequency of vibration and the velocity and acceleration of the mass when it is passing through the mid position, that means the center of the oscillation. So the static equilibrium position, that is the mid position for an oscillation, and also the half amplitude position. So when the mass is midway between the mid position and the maximum extreme position, that will be our half amplitude position. So we have to find velocity and acceleration. Third part asked is that the energy of vibration. So we'll go on solving this problem. First we'll draw a sketch. So this was the initial state. There was a spring and two masses each of 4 kg were attached to this spring, having a stiffness of 2 kilonewton per meter, and then one of them was suddenly removed. So then the system became like this. Let's say one is removed, so the only one mass is remaining of 4 kg, other is removed. Then if you see the static deflection in this case, let's say this is the position, and let's say this is the unstretched position. There will be one unstretched length of the spring, so unstretched position of spring. So in case 1 where both the masses were attached, let's say the static deflection was delta 1. So delta 1 will be equal to force extending the spring divided by stiffness of the spring. F is equal to kx. On that we get kx is equal to F by k. Force touching the spring is two masses of 4 kg each divided by 9.81. So mg is the force touching the spring. Stiffness of the spring is 2000 Newton per meter. So you get the deflection in meter, that is equal to 0.03924 meter. So this is deflection for position 1. So for position 1, static deflection is equal to 0.03924 meter. Now what about position 2? Position 2, we are talking about an instant when the first mass is removed. So the deflection will be delta 1 only. So the position will be maintained. It cannot suddenly change itself when suddenly a mass is removed. However, the equilibrium position of this new system will not be at delta 1. will not be at a delta 1 distance from the unstretched position, but somewhere a distance closer to the unstretched position. So this is unstretched position here. So there will be some delta 2, which is a static deflection for the case 2. So this will we can derive from the forces acting on the spring in this second case. Second case it will be just 4 kg into 9.81 is the mg and 2000 is the stiffness of the spring. So we'll get 0.01962 meter. So the static deflection is delta 2. Now the initial position of the mass in system 2 is delta 1 because that was the deflection under the influence of both the masses. And since one mass is suddenly removed, the initial position will not change instantaneously. Instantaneously, the initial position is delta 1. So now we can define our vibration model. So our vibration model is such that the static equilibrium delta 1 is like the static equilibrium position is at delta 2 from the unsteady position, and the initial position of the mass is at the distance delta 1 from the unstretched position. So the amplitude of vibration we know now. So the amplitude, this is the maximum displacement of the mass from the mean position. So amplitude of vibration will be equal to delta 1 minus delta 2, that is equal to 0.3924 minus 0.01962 will come around 0.01962 only, because this value is half only meter. So this is the amplitude of vibration, and that's called A. So this answers the first part of the question, half of the first part where amplitude and vibration frequency were asked. So for determining the frequency, you don't really have to worry about the initial condition. You know the system now. The system is just a mass of 4 kg hanging from a stiffness of 2 kN per meter, and you know that the frequency is equal to 1 by 2 pi of k by n. So K in this case is 2000 kilonewton per meter, and mass of the oscillating is 4. Simplify this expression. So this value comes around 3.87 Hertz. So this is the frequency of vibration. So this is answer to the part A of the question. Now we come to the part B of the question, where it is asked to find the velocity and the acceleration at mid position. So for that we have to find our equation of motion. It will be simpler if we do that. So x is equal to initial displacement cos omega t plus initial velocity at 0 divided by omega sine omega t. So this is general equation. We put our initial condition, initial displacement x0, if we take downward displacement as positive, it is equal to 0.01962, that is the amplitude of vibration, because at time instant t is equal to 0, the 4 kg mass was 0.01962 below the equilibrium position, and then it was released. One of the mass was removed and it was released. So initial condition will take that. Initial velocity, when the mass was just released, instantaneously there will be no velocity. Due to acceleration, the mass will start to accelerate. So initial velocity is 0. So 0 by because initial velocity was 0. Two masses are there and one mass is suddenly removed. This mass will take some time to gain velocity. It will accelerate, but it will take time. So you get 0.1962 for omega t. Now this is the expression for x. So x is equal to 0.01962 cos omega t. Now what about the velocity? Velocity will be equal to dx by dt, which will be 0.01962 minus sine omega t multiplied by omega. So this will be equal to minus 0.01962 omega sine omega t, and acceleration is equal to minus omega square x. or you can differentiate also, you get the same velocity, same expression. You get minus omega square 0.01962 cos omega t. So if you draw a graph of the displacement x, you will see that we are starting from the minimum position, then it is increasing and going like this. So this is t is equal to 0 position, the bottommost position of the spring mass system. And then it will start to accelerate for the top. This is the mean position. Mean position is the delta 1 position. So if you cross the mean position at pi by 2, then it will reach the maximum at pi, and then 3 pi by 2 it will again reach the mean position, and then at 2 pi it will come back to its original position. So if you want to calculate the velocity and acceleration at the center position, so we'll substitute, and we know that this is theta in phase angle. In phase diagram, you saw that the theta is equal to omega t. So we don't have to necessarily determine the t and the omega. We can, by seeing this graph, we can simply substitute the value of theta is equal to omega pi by 2. That means pi by 2 equal to omega t in this expression, and we can get. So velocity at mean position will be v is equal to minus 0.01962 omega and sin omega t. Sin omega t is equal to, at mean position, omega t is equal to pi by 2. So sin pi by 2. And omega we have to determine. Omega we know the formula is equal to 2 pi into natural frequency. So 2 pi into the natural frequency we got earlier, 3.57 hertz. So we will put it here, 3.57. So this is equal to 22.35 radian per second. So this is substitute here. Sin pi by 2 is 1 anyway. Minus 0.01962 2.35. So the velocity at mean position is equal to 0.438 meter per second in a negative direction. Negative direction indicates that the velocity will be towards the top, since x is positive downward. So the velocity is towards the top at the mean position. It is trying to come to the higher extreme position. Now what about acceleration? So acceleration, we know that it is given by minus omega square amplitude, the equation for the x cos omega t. Omega t we know it's pi by 2. So we'll put cos pi by 2, and here we'll put pi by 2. Cos pi by 2 we know it's equal to 0. So the acceleration at mid position will be equal to 0. There is no acceleration at the mean position. Everything is just the velocity, the kinetic energy. Now the other part of the part B was the velocity and acceleration at the midway position, half amplitude position between the extreme position and the mean position. That's called the half amplitude position. So if you see from this graph, the half amplitude position will occur somewhere here. From the symmetry of the sine wave or the cosine wave, it will occur at pi by 4. So in the case of half amplitude position, theta will be equal to pi by 4. So we'll substitute the velocity omega t is equal to we'll substitute the value omega t is equal to theta is equal to pi by 4. The expression for velocity, on substituting the value, we'll get this value in the equation of velocity. To simplify, you will get the answer as 0.38 meter per second. For the acceleration, you have expression 0.0 omega square cos omega t. You substitute the values. So omega square cos pi by 4. If you simplify this expression, calculate, you will get the acceleration of 4.905 meter per second square. So at the halfway, the mid amplitude position, there is some acceleration, and it is 0 at the mid position. Now the part C of the problem, find the energy of vibration. So energy of the vibration, you know that it is switching between potential energy and kinetic energy. So we know that at mid position, the potential energy mid position, that is the static equilibrium position. So in the static equilibrium position, there will be no potential energy. All the energy will be kinetic. No P, all kinetic energy. So if you determine the kinetic energy at the mid position, and we know that total energy equal to PE plus KE is equal to constant, and at mid position PE is equal to 0. So you get at mid position total energy is equal to kinetic energy. So we get total energy equal to KE mid position. So this will be half m, and velocity at mid position square. Mass we know is kg, velocity we saw is 0.438 square. So we'll get a value of 0.3844. These are SI units to joules. This is the total energy of vibration. So this is the answer for the part C. Like that, you can form very simply the equation of the motion by considering the basic equation, substitute the initial conditions, and then you can determine velocity, acceleration, energy at any instant of time. It's quite simple. This kind of questions can come in objective in the GATE examination. Now we come to the theory of viscously damped free vibration. In simple language, they are called damped oscillations or damped vibrations. So we will derive the theory of damped oscillations with the help of the spring mass system that we have considered. So in the vibration model, we showed that in a spring mass system, if you are adding a dash pot to the mass, which is damping the oscillations, you can get the viscous damping effect. The dash pot in application is a pot with a piston inside and some orifices and a fluid inside. So when the piston moves, the fluid goes from one side to another, and it results in loss of energy. So damping means basically loss of energy. This you are modeling by adding a dash pot. Like the spring mass is a representative of any system which is having flexibility to come back to equilibrium position and having inertia. Similarly, dash pot is also representative of any damping. So in the real world, damping can be of different nature. It can be friction damping, it can be air resistance damping, and there can be many manifestations of the damping. But here we are taking a simplified approach of using a dash pot, and in the dash pot, the damping force Fd is equal to is proportional to velocity, and so hence it is equal to Cx dash, where C is a constant of proportionality. So this additional force we will have to add up to our spring mass system, which is displaced. Let's say this is a static equilibrium position, and the mass is deflected x from the static equilibrium position to 0 position, and x is positive downwards. So x dash and x double dash are also positive downwards. So we will draw the free body diagram for the mass m. If you consider mass m in isolation, it is shifted x from the 0 position, static equilibrium position. So it will have a upward force of kx. Earlier we saw that k delta is equal to mg. So k delta and mg will balance and cancel out each other at all the instances of the oscillation. So only unbalanced force is kx. Static deflection and weight doesn't matter because they cancel out each other as kx. And then since you have acceleration towards the bottom, so you will have a inertial force towards the top, because inertial force is opposite direction acceleration. We are taking positive downwards, and that now the third component, that is due to the viscous damping, that comes to the velocity. The velocity is also taken positive downwards. So if we saw that the damping resists the motion, All damping always resists the motion. So the motion is in downward direction, then the damping force will be opposite to that, that is upward direction. So the Ft will be towards the upward direction, that is equal to Gx dash. So if you see in the mass m, three forces are acting: Kx, that is spring force, Fs, then acceleration force mx double dash towards the top, inertial force, and Fd, the damping force. So these three, summation of these three forces should be equal to 0. So from that we'll get our equation for damped vibration as Fs plus Ft plus F is equal to 0. That is Kx plus Px dash plus Mx double dash. The equation that we get here is a second order linear differential equation. A traditional approach of solving this problem is to assume a solution of form e to power st or e to power s into some whatever the variable. So in this case we will assume x is a function of time, so we will assume x is equal to e to power st, where s is a constant that we will determine from the equation. So if you substitute x is equal to e to power st, then what we get from our differential equation, you get k e to power st plus c x dash. X dash is d by x dash is equal to d by dt of e to power st, that is equal to s e to power st. So we will get c s e to power st plus x double dash will be equal to differentiation of x dash, that is s e to power st x dash dt, that will be x square e to power st. So we get m x square e to power st is equal to 0 from the substitution or in equation, substitution in the real equation. So taking e to power st common outside, we will get s square plus c by cs by m plus k by m. This whole thing is equal to 0. Now e to power st can't be 0 because this is a displacement in time, and we are solving for a general time, not for a specific time like for the mean equilibrium position when the displacement is 0. So this thing can't be equal to 0. So this thing will have to be equal to 0. So here we get a algebraic equation instead of a differential equation by substitution of x is equal to e to power st, and now our task is to determine the value of x. So solution of this algebraic equation will be s is equal to, so solution for any general differential equation, algebraic equation of a quadratic form is this one. As you can see, somebody called from your math class notes. So comparing this equation, we get a is equal to 1 and b is equal to c by m and c is equal to k by m. So solution of our equation will be s is equal to minus c by m plus minus root over c square by m square minus 4 into 1 into k by m divided by 2 into 1. So we'll get s equal to minus c by 2m plus minus square root of c by 2m whole square and k by m. We have taken the denominator 2 inside the square root, so it will become 4. It will cancel the 4 here and become 2m whole square here. So this is the solution for the values of x. So as you can see, we have got two solutions. One is s1, that is minus c 2m plus c by 2m whole square minus k by m, and then the other solution we will take the negative sign, that is minus c by 2m minus square root of c by 2m whole square minus k by m. So we have two roots of the equation. So s1 s2 are called roots of the equation and help to determine characteristics. That is the nature of the functions. Characteristics. So the characteristic function would be x is equal to e to power s1 t and x is equal to e to power s2 t. These are characteristic functions. So these are the two functions which define the actual solution, and the actual solution is a combination of the characteristic functions. So x will be equal to a, the first characteristic function, that is e to power s1 t, plus b e to power s2t, that is a second function. So this becomes our solution, and substituting the value of roots, we will get x is equal to a e to power minus c by 2m plus root over c by 2m whole square minus k by m t plus b multiplied with the e to power minus c by 2m minus c by 2m plus k minus k by m t. That is the second root. So this is the general solution. Here we have to determine a and b by initial conditions, like we did for the free vibrations. So we will analyze this equation now.